All right, guys, so we'll get started. I want to give out a few reminders items here, and then one announcement. So for the lab makeup, if you have any missing labs up to this point, most of you guys don't, but there's a few of you guys do need to make up your lab, one of your missing labs. I actually have four sections for makeup this week. So Tuesday, Wednesday, Thursday, and Friday afternoons. Okay. So if you are plan to coming in a section that is not your designated lab section, let me know in advance so I know that you are coming. Okay, so that's for makeup lab. Um, and then other reminders items are homework 11, which is due tonight, and then 12 is due Monday next week. Okay, and then final exam will be on 22nd, the Thursday, at 10 a.m. until 11:50 a.m. Okay, so make sure you mark those dates down. It looks like we can finish the lecture today, so you'll only get my reminder here. I may send out an email or maybe not, but you guys want to take those dates down for the coming up due days and exams, okay? And then one announcement is for the modern physics that is going to be in the fall of 2021. There are still seats available. If you any of you guys are considering getting a minor in physics, I believe that's the only extra class you have to take to get physics minor. Based on you guys are having other required classes as your major. So if you take modern physics, then you'll be getting a minor if you declare that. This is an alternating year course. So currently, so that means if we are offering it in the fall, then the next time that will be offered will be in 2 years. Okay, so make if you want to get a major in a minor in physics, just think about that. Um, there's other options that you can do a direct study with me, or you might take it at Kenyon College. So there are other options. You can let me know if you are interested. Okay. All right. So those are the reminders and then kind of announcement before we get started. So today we'll be looking into chapter 3 and 4 in volume 3 of university physics. So that these two chapters deals with the wave property of the light. So we'll take a look on that. So mainly interference and diffractions of waves. Okay, so let's take a look on that. I'm sure most of you guys, when you were a kid, you actually love to play bubbles. Sometimes yeah, and up to these days, I'm also enjoying playing bubbles with my kids. So it's amazing that when you have bubbles in air, you see all those different colors, fringes appear on the surface. Okay, so hopefully after today's class, you will be able to explain that's the case. Okay, all right. So before we get started, let's take a look on the wave aspect of the light as to get started. So light we know is a electromagnetic wave. So then it has the property of waves. So speed of the wave or speed of light that is equal to its frequency times its wavelength. Okay, and then when light enters medium, the speed is reduced by a factor called index of refraction. So then speed of light in medium is equal to speed of light in vacuum divided by m. Because of that, then actually the frequency, so when light enters the medium, its frequency will remain the same. So then wavelength will be reduced. So wavelength in medium, we can denote as lambda sub m. That means in medium has the index of refraction of m. That should be equal to the wavelength of the light in vacuum divided by the index of refraction m. Okay. A quick review on what we learned earlier on interference of waves. So if you have two waves propagating in space, when they meet, they add up algebraically. Okay, so if you have y1 as wave 1, y2 as wave 2, then the resultant will be equal to y1 plus y2. Okay, if you have two identical waves, then they will add up to be we call constructively interference. Also, if you have the two waves coming out of identical sources, say source 1 and source 2, they are synchronized. Now, depending on the location you are hearing or you are having the two waves meet at a particular location A, B, and C. So at different locations, wave from source 1 and wave from source 2 will travel, likely travel through different paths. So when that happens, then you'll have interference of waves coming out of identical source as well. Okay, so again, this is algebraic sum up of the two waves. If you have two waves coming from source 1 and source 2 meet at particular point of interest P, then they add up. Okay, algebraically. And the result is if there's a phase shift between the two, all right, if they are not exactly in phase, they are not exactly identical, then you'll get a function as 2 times cosine of the delta divided by 2, or 2 times a cosine of delta divided by 2, the phase difference divided by 2, and then a sine function similar to the original one because delta is small. Okay. So depends on the path difference delta here. So the phase difference, yeah, let me put this way. The phase difference is due to the path difference in this case, okay? When you reach at a particular point of interest in this case. So path difference, delta x, will give you the phase difference equal to k times delta x, where k is equal to 2 pi divided by lambda, okay? So then delta is equal to 2 pi over lambda times delta x, where you can rewrite it. So then delta x divided by lambda times 2 pi to be the phase difference of the two waves when they meet in space. Okay. So in that case, if you have path difference of m times of lambda, you can see delta is equal to 0, 2 pi, 4 pi, etc. Okay. So that means they will add up. Okay. So which means construct interference. And if the difference in path delta x is equal to half of lambdas, okay, so lambda over 2, 3 over 3 lambda over 2, 5 lambda over 2, etc., then the two will cancel out, resulting in the destructive interference, okay, in that case. So this is in the condition of the two sources are in phase, okay, and then if the two sources are differ by with original phase difference of pi or out of phase, then the conditions are flipped, okay, for construct interference and destruct interference. All right. So with that background, then let's take a look on the interference of the light. Okay, so if you have a light shining on a slit over here, okay, so then this light coming from this slit, okay, can propagate in space in 2 or 3 dimensional in space. Then when it hits, if there's a second plate over here with 2 small openings, 2 slits, then light will come out from slit 1 and then come out from slit 2. Okay, so you can treat that light come out from slit 1 as wave 1, and then light comes out from slit 2 as wave 2. So when the two waves meet in space on the screen here, certain distance away from the two slits, then you'll see the interference patterns of the two waves coming out of the two slits. Okay, so at some places you will see constructive interference, sometimes you will see destructive interference. Okay, so you'll see like bright fringes and dark fringes. Okay. And then if you'll be doing this in a lab, this is what you'll be seeing. Okay, you'll see like bright fringes and then dark fringes, etc. Okay, and the center here you'll get a maximum, and then you'll get minimum and maximum, minimum, etc. and in that pattern. Okay. So this is because light coming out of the two slits, they are having differences in their path when they travel through the distance from the slits to the screen and then hit the screen. All right. So in this case, if you look at the path difference of wave or light coming from slits 1 and slits 2, you'll see that most of the time, the separation of the two, or the distance between the two slits, is smaller, much smaller compared to the distance from the slits to the screen. Okay, so then for these two passes, they are almost the same, but there's a slight difference over here. So if you compare the two, if you zoom in here, then the slight difference is only this part. Okay, from the geometry, you can tell this part is going to be equal to d sine of theta, if d is the distance between the two slits, and theta is this angle theta. So this angle theta will be the same angle theta here. Okay, so d sine theta will be the delta x. Okay, so then phase difference small delta is equal to delta x divided by lambda times 2 pi. Okay, will be equal to d sine theta over lambda times 2 pi. All right. So when this phase difference small delta is equal to 0, 2 pi, 4 pi, etc., then you'll have constructed interference. You'll see bright fringe on the screen. And then when this delta is equal to half of lambdas, or in this case, it should be just pi, 3 pi, 5 pi, the odd number of pi's, etc. Okay. So then this is the condition here. F delta is equal to m times 2 pi, where m is from 0, 1, 2, 3, then you'll have constructed interference, or we call it interference maximum. Okay, so m is the order of the interference. So you can write this equation as this. So d sine theta sub m, that subscript m denotes the orders of interference. Okay, so d sine theta lambda times 2 pi equal to m 2 pi. Then 2 pi and 2 pi will cancel out. You'll see d sine theta is equal to m times lambda. Okay, for interference maxima. And yes, I forgot to put down the equation for the interference minimum. Oh, actually, oh, did I just skip one? Okay, I skipped one slide. So here, d sine theta equal to m lambda, this is the interference maximum. And then on the other hand, if this phase shift delta is equal to all the integer multiples of pi, then you'll get destructive interference, where you'll see interference minima. Okay, so d sine theta in this case then is equal to m minus 1/2 of lambda. Okay, that's the equation for interference minimum, or the dark fringe, the position for dark fringe. Okay, let's take a look the first example here. So this one says two narrow slits separated by 1.20 millimeter are illuminated by light that has 600 nanometer wavelength, and the interference pattern is viewed on a screen 2.50 meters away. Calculate the number of bright fringes per centimeter on the screen in the region near the center fringe. Okay, so this one, it gives you, let me stop sharing here and then move to the other screen. So it gives you separation of the slits, that means D equals to 1.20. So this is in millimeter. It tells you the wavelength used is 600 nanometer. Okay. Now it says the viewing screen is 2.5 meters away. So let's take a look here. Typically you have double slits here, and then you have view screen. So this is 2.5 meters. So this is L equal to that. Okay. Um, and then you'll have this as your theta. So it's looking for how many numbers of bright fringes. Okay, so you'll be using d sine theta sub m equal to m lambda for this problem. Okay, and you're looking for how many bright fringes per centimeter. So you can take 1 centimeter from the center of the screen, the bright fringes on the screen here. So let's say this is 1 centimeter. And then if you can calculate if this is 1 centimeter, what would be the number of the interference here is, then you will be able to tell how many bright fringes would that be. Okay. Now, when you have this angle as a small angle, so you can tell this is 1 centimeter, right? This is 2.50 centimeter. Okay, so for small angle approximation, we say if angle is less than 15 degree, then the angle in radians which should be approximately equal to the sine of theta. Okay, so that's a small angle, so this should be in radians. Okay, and then that should be approximately equal to tangent of theta. So that's the small angle approximation. Okay, small angle approximation. Okay, so if you can tell your angle is small, you can use the small angle approximation there. So let's take a look here. So in this case, if this is theta sub m, this let's take it that way, then tangent of theta sub m should be about equal to sine of theta sub m. And this you can see, which would be tangent of theta should be equal to 1 centimeter divided by 2.5 meters. Okay, and you can see you can put that into the equation here. You can solve for your m. Okay, because lambda is given and then d is given, so m is equal to, in this case, lambda divided by d sine theta m, or approximately equal to lambda divided by d tangent of theta m. Okay, so in that case, you can plug in your numbers here. Or actually the other way around, sorry. So m is equal to d sine theta over lambda, which is approximately equal to d tangent theta over lambda. Okay, so d is the separation of the two slits, 1.2 millimeter times 10 to the minus 3 meters. Tangent of theta is equal to 1.1 centimeter, so 1 times 10 to the minus 2 meters over 2.5 meters. Okay, and then divided by lambda, which is 600, that's in nanometers, 10 to the negative 9. So that will give you 8. Okay, so m is equal to 8. So that means you can see about 8 bright fringes per centimeter over there. Okay, now sometimes you may see m equal to 8 points, say, or in this case, actually, it's not exactly. Is it exactly 8? Yes, I think it is. Okay. Yeah, just for your reference, if you get m equal to, say, 8.5, then you are going to just write down as 8 per centimeter, okay? Because you cannot take the partial of it as a full fringe. Okay, that's on that one. All right. Questions you guys might have on this? Okay, if not, then we are going to move on to check single slit diffraction. So um, it was observed that even if you have a single slit and then you have a screen behind it, you will still see um, interference patterns or like dark fringes and bright fringes. Okay, so in this case, technically we shouldn't say interference because you don't have two slits that you can say two waves coming out of two slits. Okay, so it's just one slit over there. So why this is happening? It's because you can actually divide a single slit into very small pieces. Okay, so then there's say if a wave comes from one small slit from the top here, a distance of half of the slit size down there, you'll find another one that will have a wave propagating from there. Then it will these two waves will hit the screen and then they will interfere each other. Okay, similarly to the double slit interference. Okay, in this case, we'll take a look on the path difference of this one and this one. Okay, so if this two has a path difference, which will be represented by this 1/2 of A times sine of theta. Okay, so when that happens, and let's see. Okay, and then that's the difference you can use to locate where it will be the first interference minimum of these two sources. Okay, so if you set that up, then you'll be able to see if you take this as 1/2 lambda, that will give you the first darkness or diffraction minimum. Okay, so then for diffraction minimum, what it happens at 1/2 A sine theta equal to 1/2 lambda. Okay, so then A sine theta is equal to lambda. You can also use small angle approximation because usually this angle will be small. If it's less than 15 degrees, then you can use that. Okay. So for general expression, then you'll see if you have nth order of the minimum diffraction pattern, then you will be doing A sine theta sub m equal to m lambda. Okay, m is equal to 1, 2, 3. Okay, so this is the equation for diffraction minimum or the dark fringe. Okay, so this is because of the fact that we use this separation from two waves as 1/2 of A. Okay, then you get this equation. Okay, so this is a little bit different from two slits, double slits interference where you use D sine theta equal to m lambda for maximum interference or bright fringe. Okay, so just take a note on that. All right. Let's take a look on one example on the single slit diffraction. So this is also true in general for a wave because we kind of derive this from wave aspect of the light. So you can also apply this single slit diffraction to any other waves. Okay, so in this case, it's asking you for microwaves. Okay, it says plane microwaves are incident on a thin metal sheet that has a long, narrow slit of with 5.0 centimeter in it. The microwave radiation strikes the sheet at normal instance. The first diffraction minimum is observed at theta equals 37 degrees. What's the wavelength of the microwave? All right, so this one tells you your slit size is A equal to 5.0 centimeter. And then it says when M equal to 1, theta 1 is equal to 37 degrees. Okay, that's the diffraction minimum. So for diffraction minimum, we'll use A sine theta 1 equal to m times lambda. M is equal to 1. Okay, so it looks like we have the 5 centimeter given, we have the theta 1 given. We can solve for the wavelength directly. Okay, so then in this case, lambda will be equal to A sine theta 1 be equal to 5 centimeter times sine of 37 degrees. That will give you 3 centimeter, okay, for the wavelength. All right, questions you guys might have? So if not, then we'll move on here. So remember when we said if we have two waves, they will add up. Now, if there's a slight difference in phase, okay, so in this case, the phase difference is not originated from path difference. So if they have already phase difference to start with, okay, for the y1 and y2. So y1 is kx minus omega t, y2 then is kx sine of kx minus omega t plus delta. Okay, so if that's the case, then when the two waves meet, they will have interference with each other. Okay, mathematically you can see the expression over there. All right, and then again, if delta is equal to 0, the two will add up. It should be like 0 or multiples of 2 pi. So when there's delta is equal to 0 or multiples of 2 pi, then they will add up. Okay. On the other hand, if the delta is equal to pi or all the numbers of pi, then we call them out of phase. They will cancel out. Okay. And then anything in between, you will have partial cancellation. Okay, of the two waves. Now, also, when the wave encounter barriers, we know that, so this is again a quick review. We know that if you have wave that is propagating from a thinner material and then enters a thicker material, so part of it will enters the material and then part of it will be reflected. So in that case, if this is from thinner to thicker, then for the reflected wave, it will have a phase change of 180 degree that flips. Okay, so this also applies when you have light actually traveling from less denser material into a denser material. Then for the reflected light, it will have a phase change of 180 degrees of pi. Okay, so that happens when n1 is equal to n2 if the light goes from medium 1 to 2. Right? Now, on the other hand, if wave travel from thicker material into a thinner material, then for the reflective wave, it will not have that phase change of pi or 180. Okay, so let's take a look on if a light hits the interface traveling from one medium to another. Okay, this one says light that has a wavelength of 500 nanometer is instant, normally on a film of water of 1.00 micrometer thick. What's the wavelength of the light in the water? All right, so this is something we learned from the early of this lecture. When you have light hit the water, actually its wavelength change, okay, reduced by effect of the index of refraction. And then B asking you how many wavelengths are contained in a distance of 2 times of thickness. The film has air on both sides. What's the phase difference between the wave reflected from the front surface and wave reflected from the back surface in the region where the two reflected wave superposed. So let's take a look on this one here. So on A, so let's say this is a thin film of the water. This is 1 point, the thickness is 1.0 micrometer, or 2 zeros. This is a water film, okay? We know that for air, index of refraction is 1, almost 1. For water, is 1.33, okay? And then at the bottom here is still air. On A here, when the light from air hits the interface here, and part of it will enter the water, so it's asking you what would be the wavelength for the light in the water. So then wavelength in the water, let's use lambda sub m equals to lambda in the air divided by m, okay? So it would be equal to the 500 nanometers divided by 1.33, that gives you 375 nanometers for that wavelength in the water. B is asking you how many wavelengths are contained in the thickness of 2T. Okay, so then you'll be doing 2T divided by lambda m. Okay, 2T divided by the wavelength. 2 times 1.00 times 10 to the minus 6 in meters for micrometer, and then wavelength 375 times 10 to the negative 9 in meters. Okay. So that would be equal to 5.33 wavelengths contained. All right. Now PHY is asking you if you have airs on both sides of the water, what's the phase difference between the wave reflected from the front surface and the wave reflected from the back surface? Okay. So let's see here. When the light hits here, water surface, so part of it will be reflected. So let me just say this is the reflected, okay? Reflected wave 1. And then part of it will go into the water. And then we'll hit this surface of water and air here. And then this will get reflected. So let me just say it will reflect backward in that direction too, okay? And then the remaining part of that will enter the air down there, okay? It's asking you what would be the phase difference between these two reflected waves, okay? So for the first one, you are going from air to water. So you are going from thinner material to the denser material. So wave 1 will have pi or 180-degree phase change, okay? Now phase 2 will not, because for wave 2 here, it goes from the denser water to the lighter air. So then this second one will not have phase change, okay? So no phase change. All right. So then you can see wave 1 and wave 2, they will have a difference of phase as pi or 100 degree. Okay, so that's that. So pi or 180 degrees difference in their phases. Okay. And then in addition, for wave 1 and wave 2, there's a path difference as well. Okay, so then path difference will be 2t, delta x will be equal to 2t. Then the overall effect will be the phase difference caused by phase path difference. So overall, you'll have a phase difference of the two equal to delta x over lambda times 2 pi, okay, plus the phase change of pi in that case, okay. So delta x is 2t divided by lambda, or in this case, we should use lambda sub n, okay, because that's the wavelength. We should be considering wavelength in when the wave is inside water, okay. So that's equal to 5.33 times 2 pi plus pi, okay. That will be your overall phase difference of the two, okay. So this is overall. All right. Any questions you guys might have? All right. If not, then we'll take a look why you see different color fringes on bubbles. Okay. So you see interference patterns on bubbles is because there's very thin film on the surface of the bubble. Okay. So then because of that, the light hit the bubble surface will get reflected when it first hits the top surface, okay? And then part of it will get reflected, part of it will enter the film. And when the film hits the other side of the surface of the bubble, it will get reflected back, okay? So there's a phase difference due to first from the two waves or from the two reflected lights, you might have phase change for one of them or maybe both, okay. And then the second, there's a path difference of the two reflected light, okay. So then overall there's a net phase difference between the two, okay. So let's take a look on here. Depends on for your thin film, it depends on what's N1 and N3 and N2, N1, N2, N3. Okay, so if you have N1, so two scenarios you might be encountering here. So N1, N2, N3. If you have N1 less than N2 less than N3, so then you are going from for the instant light, part of it get reflected. Okay, ray one here will have phase change. Now the refracted ray enters the thin film here, hits the other surface of the thin film here will get refracted as well. For ray 2, this ray 2 if N2 is also less than N3, then this ray 2 will also have a phase change. Okay, so then overall these two will cancel out. Okay, then the phase difference is purely due to path difference of the thickness of this thin film. So delta x is equal to 2t divided by lambda and then times 2n or 2 pi. Again, that would be the net phase difference of the two rays, ray 1 and ray 2. Now, on the other hand, if you n2,
excuse me, Dr. Howe.
Yes.
I don't. Are you like pointing at stuff on the PowerPoint? Or
All right. Sorry, I guess I forgot to share.
it's all right. Thank you.
Yeah. And let me see. Right. So the thin film here. So let's take a look on this figure over here. So this is if you have a thin film here sitting on top of, so this could be the case for the bubble. So if this is water, and then on top of the water, your bubble, okay, on top of that, there's a thin film, and there's air here, okay. So when light instance on the first surface here, N1 is less than N2, so the refracted ray one, number one, will have a phase change of pi. For this ray enters the thin film here, it hits the second surface over here because N2 is also less than N3. So then ray 2 reflected back over here, we also have a phase change of pi. So then ray 1 and ray 2, for the phase change effect, they cancel out. Okay, so the overall phase difference delta pi then should be coming from the path difference of ray 1 and ray 2 when it hits your eye. And that difference is the twice of the thickness of the tip, because for the second ray, it travels into the thin film, hits the surface and comes back. Okay, so 2t. So 2t divided by lambda in the median, and then times 2 pi. So that's the overall phase difference. On the other hand, if you have, say, air on one side, water, and then air on the other side, so in that case, if N2 is greater than N3, then for ray 2, you will not have a phase difference or phase change. Excuse me. You will not have phase change for ray 2. So then overall phase difference between ray 1 and ray 2 should be coming from this part, which is the path difference plus phase change of one of the ray. Okay, so then you will add pi to delta here. Okay, so it depends on what you have for the index of refractions. Okay, so then either way, okay, so if you have just one of the two reflected ray has phase difference, okay, so then you have delta equal to 2t divided by lambda m times 2 pi plus pi, because only one of the two rays will have phase change. If you set that equal to 2 times m times pi, which is multiples of 2 pi, then you'll get constructed interference. Okay. On the other hand, if you have both reflected rays have phase change, so then phase change effect will cancel out. You'll only have phase difference due to path difference. So then you'll set this delta 2t over lambda sub n times 2 pi equal to 2 times or m times of 2 pi or 2m times pi. So multiples of 2 pi. So then you'll get the constructed interference. Okay. So that's the condition there. You can also see this effect by looking at if you have two glass slides, assuming they are clean on the surface, there's no thin film on the surface. Okay, if you intentionally put a small gap between the two slides, okay, then there's a thin layer of air. So in the figure A here, if you zoom in into between the two slides, you'll see here on figure B here, there's a thin layer of air in between the two glass slides. Okay, so then in that case, when light hits the surface here, all right, enters the first glass, get reflected. Okay, for ray 1, that ray will not have phase change. For a second ray, hits this air here and then hit the glass here. Ray 2 will have phase change. Okay, so the two will have phase change, and then plus the thin air there, you'll see. So in that case, you also see diffraction interference patterns, like some colorful fringes forming if you put two slides together, but leave a small gap between two. Okay. All right. Sometimes you'll also see this fringe only on one piece of glass. Okay, this is called Newton's rings. All right, so then that's similarly, if you have a light hit on the first surface, get reflected as ray 1, that will have phase change, and then the second one hits the other side of glass and then get reflected. So you'll have two rays coming off two surfaces, and then they will interfere with each other. Okay. So let's take a look on one example on thin film interference here. This one says a film of oil that has an index of refraction of 1.45 rests on an optically flat piece of glass with an index of refraction of 1.6. When illuminated with white light at normal instance, light of wavelengths 690 and 460 is predominant in reflected light. Determine the thickness of the oil film. So let's take a look on this one. So this is your oil thin film. On top of it, it's air. And then at the bottom here, there's a glass, piece of glass here. Index of refraction for air, I'm going to call it N1. It's 1.00. Index of refraction for the oil, I'm going to call it N2. That is 1.45. And then index of refraction for the glass is 1.60. Okay. So let's take a look on the instant ray here. So let's say this is the instant ray comes in, part of it will be reflected. So let me call this as ray 1. And then part of it will enter the thin film and hits the second surface and then get reflected back. Okay, so it actually will get reflected right back in that direction. Then that's ray 2. Okay, so let's examine the two refracted rays, ray 1 and ray 2. Now part of it will enter the glass anyway, so that will happen, but we'll just focus on ray 1 and ray 2. So for ray 1, because you are going from N1 to N2, N1 is less than N2. So ray 1 will have phase change, okay, of pi. Ray 2, you are going from N2 to N3. N2 is less than N3. So then you will also have phase change of pi, okay. So in that case, then the phase change or phase difference between ray 1 and ray 2, the two refracted rays, will be delta equal to from path difference to thickness over lambda m times 2 pi. Okay, so this part is from the path difference of the two rays. All right, and then as I said, there might be or might not be a second effect from the phase change of one of the rays. Okay, in this case, you have both rays have phase change, so then that will be 0. That will cancel out. Okay. Now, if we would have only of them have phase change, then you'll add pi here. But in this case, there's no effect of that. So this is from phase change of the reflected rays. Okay. In this case, you don't have that. Okay, it's either 0 or pi. Okay, that's not the case here. All right, and then it says the light have 690 nanometers and 460 nanometers are predominant. That means they will have construct interference with each other. So then this delta is equal to 2m times pi. Okay, so you'll set up that 2t over lambda m times 2 pi equals 2m times pi. All right, so you can see the 2 pi here and 2 pi there can cancel out. Okay. Now lambda n is equal to lambda over n. In this case, n2. Okay. So it's lambda over 1.45 if you want to put that way. So then this equation will become 2t divided by 1.45, or actually, I'm sorry, lambda over 1.45 equals to m. So then this will go up. So because 2 times 1.45 will be 2.90 t over lambda equal to m. Okay. Now you're looking for the thickness. Okay. Now you have two equations here. You have you can apply this condition to the 690 nanometer wavelength, and then for one time, and then you can apply. So this is one time. This is the second time. You can apply this also to the other wavelengths of 460 nanometers. Okay. So you can see. So this is lambda equal to that, and lambda equal to that. So you can see if you have lambda equals to 690, then your m will be smaller than the lambda will be equal to 460, right? So that indicate for this wavelength, you'll get higher order of interference. For this, you'll get lower order of interference. Okay, so that means if you do, so on this one, 2.90 times t over the thickness over 690 nanometer, you'll get interference order as m plus 1. On the second one here, 2.90 t divided by 460 nanometer, you will get the order of interference as m. Okay, so you have this equation and then this equation. So you have these two equations. There are two unknowns in them, so m and t are the unknowns. You can solve for m and t, both of them. Okay. So to do that, you can do substitution. Okay, so you can substitute like m as this guy into there, and then you can solve for that. Okay, I'm going to do a trick here. So if I do equation 1 divided by equation 2, then what I get is left side equation 1 over this guy should be equal to this over this. Okay, so if I do this over that, 2.0 t, 2.90 t, 2.90 t will cancel out. So then I will have 460 over 690, right? Because this is denominator under the denominator, so it flips up. Okay, and then this is still denominator in the numerator still remains. Okay, that would equal to m plus 1 over m. Okay. Now I know for 460, this is 230 multiplied by 2. On this guy, this is 230 multiplied by 3. Okay. So you'll see then, let me see, I think I got something wrong here, sorry. So if I do 2.90 divided by a larger number, I should get small order of interference. So this should be m, and then this guy should be m plus 1. The same 2.09 t divided by a small wavelength, that should be m plus 1. Okay, so then I will have this as m, this as m plus 1. Okay, so with that, I can see that this is 230 and 230 will cancel out. This is 2 over 3 equal to m over m plus 1, right? So then you can see that m is equal to 2. Okay, so once you figure out your m equal to 2, you can take either equation 1 or equation 2 to solve for your t. So put that m into equation 1, you'll get 2.90 times t over 690 nanometer equals to 2. All right. Then you can solve for your t from there. So t will be equal to 2 times 690 over 2.90. That would be equal to 476 nanometer. Okay, that's the thickness of the oil. Okay. Any questions you guys might have? All right.
Excuse me, Dr. Howe.
Yes, go ahead.
Is this kind of familiar, or is this similar to what happens like if you're on a road that has like I presume like a layer of water? Is it something similar happening with the light?
Right. So usually it happens when you have a layer, say, of like oil on the surface, then you'll see that pattern. Yes. That's the
Okay.
thin film, yeah, interference.
Thank you. I was just curious.
Yep. Okay. All right. So if not, then I think that would be it for the lecture. So we've finished the lecture part. So then for the remaining lecture time, you guys can use them as your study time. Okay, so we will have exam again the Thursday next week, the 22nd, and that's at 10. Okay, and then also for you guys came in late, missed the reminder items, you want to go to the first slides of today's PowerPoint to see the due dates for the homeworks as well, and then also for the makeup lab. Okay, so if I don't see you guys for the makeup lab, I will see you guys next week on Thursday for the final. Okay, I'll be still available if you have any questions. You can come in into my office for questions, or we can set up a Zoom meeting. Okay, but let me know in advance so we can arrange that. Okay, so see you guys next week.